maybe do these ones first, right? Like, so let's make this a homework. Prove these, okay? That would be a good homework for you guys. Yeah. Now, something that's less obvious is the chain rule. There is also a chain rule for manifolds. I don't know if you guys know or not, like the multivariate chain rule. Well, it essentially comes up in Calc 3 when you're looking at like the Jacobian determinant stuff. That's pretty close to this topic, but I may be just defining something that you don't know with something else you don't know at the moment. But so sorry. So let's see here. Well, I'll write down the chain rule. I may not have time to prove it, but I have time to at least write it down. It's very natural, the formula. Like you'll be able to remember, if you see this formula and you see the pattern, you will remember it. It's very, very natural. So here's the chain rule. It's partial f, partial y, I at p is equal to the sum j equals 1 to n of partial f, partial x sub j at p times partial x j partial y I at p. So that's the chain rule. And so let me end class with, what is a diffeomorphism? Right, so let's just talk about that just a minute here. What is a diffeomorphism? Well, a diffeomorphism is a diffeomorphism between two manifolds, right? It's a smooth map between the two manifolds with a smooth, which is a bijection with smooth inverse. So like f, if we have f from m to n, bijection, and f is an element of the smooth maps from m to n, and f inverse is a smooth map from n to m, right? Then f diffeomorphism. So let me show you, this is like super cool. If we look at the map epsilon, that is defined by sending x1, x2, xn, it maps to x1 cubed, comma, x2, xn, all right? All right, so on the one hand, we can have psi from Rn to Rn, where we got psi of x equals to x. All right, we can also talk about phi from Rn to Rn, where phi of x is equal to x1 cubed, x2, xn. These are both global charts on Rn, but for the reason I started talking about class today with, they are not compatible. Because that cube, when we try to invert it, we get a cube root, which shows you that it's not like the inverse of phi with respect to the usual notion of smoothness on Rn. It's not smooth, right? Because it's a cube root, which is not differentiable at 0. But so these, if we take Rn paired with the identity map, and we take Rn paired with this cube map, that gives us two different differentiable structures on Rn. But here's the thing. They're the same in the sense that they're diffeomorphic. What's the diffeomorphism from Rn with the usual usual smooth structure, and Rn with the weirdo cube smooth structure? Jeffrey Lee says that epsilon, this map here, is, you like what I'm talking about, Jeff? Yeah, it's cool. I like this development. If we had a John in here, it would just be perfect. All right, so take it. You'll have to take it then. Ernesto's actually Spanish for John. I wouldn't know, right? No. Jack. Oh. So allegedly, this right here defines a function from Rn to Rn, right? Where if we look at the local coordinate representatives of this with respect to taking, so this defines M, this defines N. This is the chart for M, the chart for N. F mapping from M to N, where F of x is equal to x1 cubed, x2, xn. The claim is that that's a diffeomorphism. All right? What do you need to do to check that assertion of Jeffrey Lee?
It's a bijection.
It's a bijection? So how about the bijection? Can you guys tell me the bijection? What's the inverse of this map? What's F inverse of y?
The square root of the cube root.
Yeah, cube root of y1, and then everything else just the same. So there you go. There's its inverse. It's a bijection. Woohoo! Now you need to check the local coordinate representatives of those maps and show that they're smooth. What are the local coordinate representatives of those maps? So what we'd have to do for F, what's the local coordinate representative? We got to go. Have I erased them all? But tell me, which one was it? Was
It's y.
I'm nothing without this picture.
Y composed F composed this.
This is psi, and over here is my quote-unquote phi. So one of the maps I got to look at is phi composed with F composes psi inverse. What is that? Phi composed with F composes psi inverse is equal to phi of F of what? Psi inverse is, x. All right. I guess I should put x into here. All right, but then that is phi of x1 cubed, x1 cubed, x2, xn, right? But then that is x again. Because you do what? You do the cube root of x1 cubed, x2, xn, which is equal to x. And you can check the other one as well. Right? You can check the coordinate representative for the inverse function and show that there's only one to check, by the way. Because we have proposition 1.55, which means checking an atlas is enough. Now the maximal atlas for M or N has many, many more charts, but we don't care. We have proposition 1.55. It suffices to check this. And these charts cover the whole shebang, so that proves it's a diffeomorphism. Which proves that Rn with the standard smooth structure and Rn with the weirdo cube structure are diffeomorphic. They're the same smooth structure in that sense, even though the chart of the one is not compatible with the charts of the other. So this is something subtle. And like I mentioned to you guys, it's been proved that there is up to diffeomorphism only one smooth structure on Rn for n not equal to 4. And when I say that, what I mean by that is if you take any two smooth structures on Rn for n not equal to 4, they are diffeomorphic.
You mean less than 4?
No, and not equal to 4. 1, 2, 3, 5, 6, 7, forever, ever, amen. But our 4, there are infinitely many non-diffeomorphic smooth structures. Our 4 is a wild world. That's the world we're living in. Anyway, I shut up.